There are three different types of calculations one should be able to perform when titrating sodium hydroxide and the weak acid, acetic acid. In this set of slides, we're going to look at the type 2 type of calculation, which involve determining the pH at the equivalence point in the titration. The words for the problem could be something like this. 45 milliliters of acetic acid is titrated with 0.250 molar NaOH, the very same solutions that were used previously. However, in this case, the question is, what is the pH of the solution at the equivalence point? Now, something worth noting about this is that we're not really given any volume information except for the initial volume information of the acetic acid. That is, that we had 45 milliliters of it. Now, as you should recall, as we look at pH and how pH changes throughout a titration like this, the pH does dramatically at one point increase. And that point, halfway up the steep slope, is what's known as the equivalence point. And more importantly, at the equivalence point, that point that we're asked to determine the pH, the moles of the acetic acid are exactly equal to the moles of sodium hydroxide, which is to say that the acetic acid has been now perfectly neutralized by the sodium hydroxide. Just enough sodium hydroxide has been added to neutralize the acetic acid. And our goal is going to be to determine the pH at this point. The way to proceed is to look at the moles. Usually a very good idea in problems like this, and we certainly have enough information about the acetic acid to determine how many moles of acetic acid we have. Its concentration was 0.300 and the initial volume was 0.045 liters, giving us that we have 0.0135 moles of the acetic acid present initially. Now recall that at the equivalence point, the number of moles of acetic acid must equal the number of moles of sodium hydroxide. And so recognizing that this is a one-to-one relationship tells me immediately that this too must also be the moles of sodium hydroxide that have been added. So by determining the number of moles of acetic acid initially present, we can determine the number of moles of sodium hydroxide required to reach the equivalence point because these two mole values are actually equal to one another. We can also determine how much sodium hydroxide was required to reach this particular point since we already have the concentration of the sodium hydroxide and now we have the number of moles. Moles divided by molarity for the sodium hydroxide will give us the number of liters that we need to reach this point and to deliver 0.0135 moles of sodium hydroxide. Doing this division tells us that 54.0 milliliters of sodium hydroxide will be just enough to reach the equivalence point in this titration. Lastly, it will be important for us to know in a little while what the new total solution volume is. After all, we started with 45 milliliters of acetic acid, and we've just added 54 milliliters of sodium hydroxide to reach the equivalence point, and so it'll be useful information to know in the next slide just how much volume we have, and 45 plus 54 gives us 99 milliliters of total volume at the equivalence point. Just to review, at the equivalence point, the moles of the weak acid will be equal to the moles of the strong base. And by determining the number of moles of weak acid we had initially, we can also determine the number of moles of sodium hydroxide, there in step 2, as it's a 1-to-1 ratio, and then using that moles and the concentration of the sodium hydroxide, we can determine the volume of sodium hydroxide in step 3, and finally the new solution volume at the equivalence point in step 4. We're working on a type 2 equivalence point calculation problem where we're being asked to determine the pH of a solution once it's reached the equivalence point. And in the previous slide, we looked at how the sodium hydroxide that's being added to the weak acid neutralizes the acetic acid and how we can determine exactly how many moles and how many milliliters of the sodium hydroxide is required to reach that equivalence point because, and this is important, at the equivalence point, the number of moles of sodium hydroxide, well, that's equal to the number of moles of acetic acid that we started with. So what we're going to do is we're going to look at this reaction as, at first, a neutralization takes place. And to do that, we'll recognize that initially the number of moles of acetic acid that we started with, this was determined by using the initial volume of acetic acid and its concentration, why that number of moles is 0.0135 moles. In a neutralization reaction, we won't worry about the water or the hydronium now for the time being, but we will recognize that there are no acetate ions present until the neutralization begins. Now, the neutralization takes place when we add sodium hydroxide. However, at the equivalence point, we know that we're adding the same number of moles of sodium hydroxide that we have moles of acetic acid. That's the whole point. We're going to neutralize all of the acetic acid. Now, this will in turn generate the same number of moles of acetate ions on the right-hand side. Everything is a 1-to-1-to-1 relationship. And then we can calculate the number of final moles that we have. And of course, at this equivalence point, all of the moles of acetic acid have been neutralized because we've been careful to add just the right number of moles of sodium hydroxide. But then we will have 0.01350 moles of acetate ions left on the right-hand side. This is the neutralization part of the reaction. It's just keeping track of the moles that we had to begin with and how those mole values change as the neutralization is reached, specifically now at the equivalence point. Now, the next thing that we need to do is have a look at the equilibrium part of this problem. And we'll do this using the standard ICE problem-solving format. Now, for the acetic acid, why none of the acetic acid was left. As a result, its concentration will be 0. And as far as the hydronium ions are concerned, we'll assume they're 0 as well. Of course, the water is left out because it's a pure liquid. And then the acetate ions are present in a great amount, having been produced as a result of the neutralization. And we can calculate their concentration by dividing the number of moles by the total volume in liters, and we'll come up with 0.13636 molar for those. So we have initial concentrations of everything that we need to solve this equilibrium problem. The next step, though, is to determine just in which direction will this reaction shift. And here we have a problem, because as you can see, on the left-hand side, we don't have a concentration of acetic acid molecules, and on the right-hand side, we don't have a concentration of hydronium ions. And this is a problem, because as we've seen in past equilibrium problems, you can't have zeros both on the left and the right-hand side. In fact, in this case, the equilibrium can't shift to the left and it can't shift to the right. And this is very typical of equilibrium problems, at least as they initially develop at the equivalence point, this type 2 equivalence point calculation. And so we've got a problem, and that is that the equilibrium, at least the equilibrium we've considered up to this point, cannot shift to the left or to the right, even though we've done all of our calculations right. Now, this doesn't mean the problem is unsolvable. In fact, it is very solvable, because as you should recognize, we have quite a high concentration of the conjugate base. The acetate ion concentration is at 0.136 molar, and there are a lot of them there. And they're floating around in a container filled with water molecules and bumping into water molecules all the time. And what this means is that these acetate ions can interact with the water molecules and involve themselves in a weak base equilibrium reaction, which looks something like this. Here we see the acetate ions. They bump into a water molecule, but instead of producing hydronium ions, they produce hydroxide ions and a small amount of the acetic acid on the far right-hand side. Now, let's look at how concentrations work out here. We don't have any calculations that we need to do at this point because we have all of the concentrations that we need to solve this new equilibrium problem involving the weak base equilibrium of acetate. Its initial concentration is 0.136, calculated above. We're not going to worry about the water, but we will assume that the hydroxide ion concentration is 0 molar and that the initial amount of acetic acid is also 0. Remember, we had neutralized all of these acetic acid molecules with a very specific amount of NaOH, and so their levels are 0 to begin with. And in this case, it becomes quite clear that with both zeros now on the right-hand side, this is an equilibrium that can shift to the right. And that's how we'll proceed in solving for the pH of this solution in the next slide. We're determining the pH of a weak acid solution as it's being titrated with sodium hydroxide, specifically at the equivalence point. From the previous slide, we found that at the equivalence point, as a result of having neutralized all of the acetic acid with an appropriate amount of sodium hydroxide, we were left with an equilibrium problem that couldn't be solved. However, by reframing the problem as a weak base problem, we have an equilibrium problem that now can be solved. On screen, you can see on the left-hand side, the acetate ion's concentration is 0.136 molar. This was produced as a result of the neutralization that took place previously. And the product species, hydroxide and acetic acid, are both zero to begin with. Now, the equilibrium part of this problem requires us to determine the direction it shifts, and it clearly shifts to the right with zeros both on the right-hand side, letting us determine that the amount of acetate ion on the left should go down by an amount x, and that the hydroxide ion and the acetic acid concentration should go up by x, giving us equilibrium concentrations of 0.136 minus x and x and x. All right, so far a very solvable equilibrium problem where we would then employ the law of mass action. For this problem, the law of mass action is a little different from weak acid equilibria. This is a weak base equilibrium where the concentrations of the products will be the acetic acid on top and the hydroxide ion on top, and the concentration of the reactant will be the acetate ion on the bottom. And substituting the values, the equilibrium expressions for these species into the law of mass action gives me an x times x, or x squared, on top, and 0.136 minus x on the bottom. And this all has to equal, very importantly now, K sub B. We were given K sub A for the weak acid equilibrium, but this is a weak base equilibrium, and we cannot use a K sub A value where a K sub B value is required. However, getting the K sub B value is relatively easy because you only need to remember that K sub B is equal to K sub W, a value that we know, divided by the K sub A value, something that we were given. Substituting 1 times 10 to the minus 14th for kW and the provided value of K sub A, 1.76 times 10 to the minus 5th, tells me that the K sub B value would be 5.68 times 10 to the minus 10th. This is the equilibrium constant now for the equilibrium problem, the weak base equilibrium that we're solving. Very important to have the KB value when you're solving a problem like this. So, the arithmetic that we have looks something like this. We have x squared on top and 0.136 minus x on the bottom, and a very small equilibrium constant that favors the reactants. And we start with entirely reactants in this problem, and so we don't expect a very large shift to the right. And this tells us that our x is equal to 0 assumption is going to be valid, and that we can very easily solve for a value of x, and that value of x will come out to be 8.8 times 10 to the minus 6th. So, a type 2 equivalence point calculation required us to look at the weak base equilibrium of the acetate ion, and in solving the ICE problem for this, we were able to determine that x would be equal to 8.80 times 10 to the minus 6th molar. Now, as you refer to that equilibrium above, note that x is in fact equal to the hydroxide ion concentration, and this is what lets us move in the direction of finally determining a pH for the solution. Recall that the pOH is equal to the negative logarithm of the hydroxide ion concentration. And now we know the hydroxide ion concentration. So we can substitute 8.80 times 10 to the minus 6th into that logarithm and determine that the pOH for this solution is 5.0554. Again, the numbers in red reflect the significant figures, and that as pOH is the result of a logarithmic calculation, the significant figures are those digits that follow the decimal point. Thus, 0.55 are the 3 significant figures required in determining the pOH. Now, the pH can be easily determined, once we know the pOH, by simply subtracting from 14. And 14 minus 5.055 gives us a pH of 8.944, with, again, 3 significant figures. So we've determined that the pH of this solution is 8.944 at the equivalence point. good. Now, some things that you would want to keep track of and go back and double check would be to make sure that your answers are correct. Substitute the equilibrium concentrations into the law of mass action and make sure that what comes out are appropriate K sub B values. Another thing to do would be to check the 5% rule, something that with such a small equilibrium constant, I'm quite confident is going to be satisfied in this case, but it's always a good idea to go back and check. And then lastly, a point about this value for the pH at the equivalence point. You may recall from your introduction to chemistry courses that the pH at the equivalence point should be equal to 7. And this is in fact the case when you are titrating a strong acid with a strong base. Strong acid and strong base equivalence points will occur when the pH is equal to 7. However, in this case, what we have is a weak acid and strong base equivalence point. And in these cases, the equivalence point will always be at pHs greater than 7.